think that pretty much ends that section. Oh, example 5 in section 16.3. What was nice about this problem is it's dx dy, not also. If it was dz, this would not have just been g of y, this would have been g of yz. But this process is the same, it's just going to be a little bit longer. Right, so example 5 is a good example of how to make that process go a little bit longer so you capture all the parts that you need. Once you understand the process, though, it's so nice. I mean, it's almost too good to believe, but if that's true, it should be too good to believe. Okay. So you got to try some of those out. This is section 16.3. So it was only about the fundamental theorem of line integrals, but it had a lot of definitions and little stuff that happened inside of it. Then you have to use one of the methods we've talked about before, right? So there's still stuff you could do. It's just not going to be as pretty as it could be. Yeah. In fact, I think some of the homework, let's see if I'm right. No, that must be in the next section. It asks you to do it both ways. Oh, that's the next section. Okay. Yeah, they could ask you. We've been doing these integrals before this section, right? So yeah, we have ways to do it. It's just they can get really ugly really quick. So this is a really nice thing to do in certain situations. Now, Green's theorem. Green's theorem I have on here really quickly. There's not much there. But there's a lot there. And let me tell it to you like this. If integrating the derivative of a function is related to evaluating the endpoints of the function, and endpoints, when I talk about a two-dimensional region, translates into what? Endpoints translates to what when I talk about regions? You can do it. It's not the endpoints of some line, it's going to be the boundary of some region. I like it. So what's really cool is that's basically what Green's theorem says. It says if you want to find, so for example, if you want to, let me see if you guys can get this. How did I write it for myself before? Here we go. So recall this. All right. That's easy shit, right? So now, let me make sure I get all this stuff down. Now, good Lord, I'm not going to write all this stuff because you can't even see what I'm writing. I've got it all written down under Green's theorem. C has to be positively oriented. That's a definition I forgot to put up there. Positively oriented just means that as you traverse it, you go counterclockwise. And sometimes that can get difficult when you're like going back on yourself in some weird-ass region. But basically, as you're moving, it should the region that you're bounding has always got to be to your left as you're going around it. That's what counterclockwise would mean. That's what positive orientation actually means here. You guys kind of with me? So if I'm going around it this way, if I'm going around a region this way, then isn't it always going to be on my right? So that's wrong. That's not right. Oh, yes. Oh, it's horrible. Too bad. I like it. It is not correct. I like it. So positively oriented path is as I'm going around a region, it's got to be to my left. So I have to be going this way. So I have a nice picture of it on page 1136. So if I have some region, I would go this way. That would be positive orientation. So I think you guys remember the direction that you go changes your answer, right? That's all this is for, really, is to make sure that this works the way it says it does, as long as the path you're taking is positively oriented. I like it. And You got a piecewise smooth. What the hell does that mean? That means, at least in pieces, this thing doesn't have any kinks to it. It's differentiable everywhere. Does that make sense? So, in 180, you could do an integral of a function that, you could do the integral of a step function, and it's nowhere near as hard as what it maybe first looked like, because it's just rectangle, rectangle, rectangle. Who cares, right? So you can have things that aren't connected. Let me not use that word. You can have things described in pieces, but the integral doesn't care really. So that's what piecewise smooth means. In the parts, this function that's in the parts has to be smooth, has to be differentiable. All right, what would just not be smooth would be that little kink thing where things get really freaky. Right? You don't want to be on that plane because you're all dead. Bam! Where am I at? Oh, simple closed. Right? So simple meant that a simple curve means that it doesn't cross over itself. Right? Simple closed. I described to you simply connected. Simple curve. Simple closed just means, let me see if they have a picture of it. It really doesn't matter that much, but do they have a picture of simple closed? No. That's good. But it's simply closed. Closed means it has its boundaries. Right? And simple means that it doesn't cross over itself. Blah, blah, blah. Oh. And of course, P and Q have to have continuous partials on the region that I'm talking about.
Is this issue 4?
Yeah, Green's theorem. Yeah. So now what we have, let me do this the backwards way first. I think that's the way I want to do this. Oh. Yeah, I like it. All right. So this is kind of like the next level integral. This is a single integral. This is a double integral. The inside of this, the very inside, is obviously derivatives. So it's going to be related to this because this is over the whole region, right? So I really want to. So this is D. This is this region that this curve, and this is C. The book uses some weird little notation. I'm going to try to stick with C. It uses both. Yeah, C is always going to be that curve. It's always a curve, and it could meet back on itself, which then defines a region. But it's still a region that's enclosed by some curve C. Okay. So here I am integrating over some entire region, but I'm integrating derivatives of stuff. So that should make sense that somehow this is going to work out to be a single integral of the things themselves. And sure enough, it comes out to be that. It's crazy. So there is a very truncated, kind of heavily assumed proof of this on page 1137. The actual proof is remarkably disgusting, and you can't even really prove all of it until you've gotten a little bit further in the book. But they do have a bit of a proof, and the proof they give, they have to assume that it's a nice region. I don't know if you guys, I never made a big deal about type 1 and type 2. Some of you guys seem to, but who cares what it's called as long as you can do it. But if it was a region that's both type 1 and type 2, that's the assumption they make, then all the work gets real easy. And then actually they just use the fundamental theorem of calculus directly in one of the steps. So what's nice about this proof that's on page 1137 is you see the connection in the proof with the fundamental theorem of calculus. So if I were you, I might look through it. But to me, it's very heavy assumption to make. But the actual proof is a little beyond us at this point. So the way we normally work this, to be honest, is the way that you wouldn't think we would work this. I think I told you I put it up backwards from where it's normally used. Sometimes it's used like this. But to be honest, more times it's used this way. Which is kind of counterintuitive. You would think we'd take double integral and get it down to 1. But to be honest, the way that works most of the time when you're going to use this thing is to go the other way. It actually makes it easier. So let's see. Let's try an example out. Let's just pick one out. Oh, that one's kind of nice. So if you do, let me see what I want to say. I want to point something out. What was the check to see if something was conservative? I might as well point this out right now, so some of you guys might have realized this. How did we just check? So here was P, we had the integral of P dx plus Q dy. We had to check if partial of P with respect to y, is that equal to partial of Q with respect to x? Now, so if it's conservative, right, this is going to equal 0. Of course, the integral of 0 is 0. I like that. Right? Or some constant maybe, but yeah. So that's an immediate usefulness of this, if I know it's... but we already kind of know that. We knew that already. We said that this around some closed path, that's really what's brought us into this. It's a closed path, right? A closed region. We already knew that if it's conservative, it's going to equal 0. But this really just puts it in your face. There it is. That's why it's 0, because there's the check. I like it. Let's do one. Let's see. Let's do one. This one looks really, really gross. Oh, and they have a little bit of a change in notation. A little bit. Not a change, but just to make it more clear. The positively oriented thing is kind of a big thing. So they have this symbol they use. You might have seen that in... There you go. I like it. Physics, some other formulas. You'll see that. And all it means is it's a guarantee that, yes, the path you're taking is positively oriented. Right? And it's closed. I like it. So this is the closed, positively oriented line integral. Where'd it go? Here it is. All right. This is so yummy. Now, I want you to realize something. I really, really want to make this distinction. If it is conservative, that means that when I go around a closed, it's going to come out to be 0, and you can see that right there. That does not mean that, bless you, this is true as long as all those little things I've got down there under Green's theorem are true. Are you with me? So it doesn't have to be conservative for this to be true. If it is conservative, it's freaking 0. So that's a special little case. As long as all this positive orientation, piecewise smooth, simple closed, P and Q have continuous partial, as long as all that's true, you can do this. So tell me, that guarantees part of that. Are these continuous functions on their domains? Yes, cool, I like it. Do they have continuous partials? Yes. On the yes, I like it, right? Because that can't be 0, for example. That's kind of nice. All right, so then I can do it. I can use this. So isn't this, like I said, it's going from here to there. Because look at this. Just look at it. Do you want to use anything on this thing? No, you just want to just not even believe this is even a question somewhere. But the reason this is easy is because it matches all those requirements. So what actually happens is this. So I can rewrite that as a double integral. We still have to talk about, we'll talk about that in a minute, what this becomes. It's pretty simple. Let's not focus on that yet. dq dx. What's dq dx? What's q? Let's start there. This guy, maybe the second PQ. It's crazy, alphabetical. What's dq dx? No, what's dq dx? 7. 7. Minus dp dy. 3. dA. So it's 4 times the integral dA over that region. Now, what would this integral be? I haven't even put the limits on there. Let me just put d down here again. What is that integral going to be? The area of the circle. The radius is 3. R squared is 9. So pi r squared is 9 pi. So this is going to be 4 times 9 pi. 36 pi. I didn't even have to figure these out because the region I was integrating across was so easy. And obviously because the inside was just constant, right? I mean, that's really the reason I didn't have to do anything else.
If you had to do it, you would go...
Yeah, if I add something inside, if it's like x inside or something, then I'd have to actually set the region up, change it to polar in this case, right? We know how to do that. This one was just so excessively easy because the inside's constant and the region's nice. All right. So one level of student right now is, I don't know what the hell has happened since the beginning of today. So, yeah, there's a lot of shit up there right now. Okay, so there's some students like that. Another level of student is, okay, I kind of follow what's going on, but wait, what the hell happened to sine x and square root and y to the fourth and all that bullshit? What then did it come into play? Well, I'd ask you the same thing about, a Math 180 problem. It's got all this weird loop-de-loops, and all that matters is the endpoints. That's all that matters. So this is just that idea pushed into 3 dimensions. So you can have even more weird shit happening inside the thing. The exact same reason it didn't matter in 180, you just had to look at the endpoints, is the exact same reason here that I only have to look at the boundaries, really. Meaning this, right? It's freaky, I understand. I agree with you, but it's a beautiful freaky. I really want you to understand. If this wasn't a closed curve, this whole thing goes to shit, right? Right? If one of these didn't meet one of the requirements, or if it wasn't going around the right way, or anything, the one little thing throws the whole thing off. So a lot of things had to be true. That's why it shouldn't be too surprising that it comes out so nice. Yeah.
So what does that symbol mean again?
So this guarantees that it's positively oriented closed path. Yeah. Because what do you require again? Positively oriented, piecewise smooth, simple closed curve.
So once we see that symbol in the problem, we just immediately know that.
Yeah, and then you just have to make sure that it's not a freaky thing where they threw something that's not differentiable or something at some point. Right? But both of these are differentiable, both of them are continuous in the region that we're talking about.
So if it's asking, like, for example, for the same thing, but that symbol's not out there.
Oh, then they have to give you more information about the path itself then. Here they just told me it was this. They have to tell me which way I was going. Right, so they'll give you like vertices on a triangle and they'll say from 1, 0 to 2, 1, whatever. You just got to make sure that it's positively oriented. That as you follow it, it's to your left. Yeah. So there will be problems like that. This one, they had to say this because they didn't say much here. Yeah.
Can you, real briefly, how did you get the curve I squared plus y squared?
Oh no, it's given. It's given. They got to give us that. That's where we're integrating across. They have to give me that.
So where does the experiment?
The first thing we did, so this whole line here is the problem.
Right.
And the first thing we did was we first verified real quick that it looked okay, and then we threw it into this format here.
Okay.
All right, I like. Now this is obviously a bit of a contrived example. I love it because they try to make it look disgusting as hell, just to really put in your face that this is kind of counterintuitive.
The end, I make it for you. 4 times 9 pi.
Yeah.
Where are we? I'm sorry.
4 times 9 pi.
Oh yeah, 4 times 9 pi. 4. And then this is just going to be the area of the circle. Now again, you could set this up and you could do it, but that's why some of the problems earlier were sketch this out and then do it geometrically. No calculus, just geometry problems. Why do they ever have that kind of problem in homework? Oh, because of this. Because I don't want to do all this work when it's just a freaking area of a circle. So you want to watch out for that kind of thing. It's not going to happen all the time, but it will happen sometimes. Let's do one more example of that, I think.
So,
what time we got?
do you have to check if it's conservative first?
No. So again,
You're not.
it has to be a closed path, right? If it was conservative also, then this would always be 0. So this itself has nothing to do with it being conservative. Nothing. It's just like, oh, but this, if it was conservative, it would be 0. That's the only place conservative comes in this at all. So there's no requirement for it to be conservative for this to be used.
Well, it's going to be good, like, to check if it's conservative before doing all this.
Yeah, because you could have some really ugly shit in here, and then it comes out to 0, and you're like, oh man, could I have? Maybe it's just a conservative shit, right? Now, if you do the integral and it comes out to be 0, does that mean that your vector field was conservative? No. Why not? Because how many ways can I start at A and come back to A? And aren't some of those probably going to end up with 0, even if it's not conservative? All right, so you got to be careful. It doesn't work both ways on that one. Just because the integral comes out to be 0 doesn't mean it was conservative. You're like, oh man, what an integral. No, maybe it just came out to be 0, right? All right, maybe. Okay, all right. So, I by the way, I know we're doing a lot today. My plan is to get a decent amount out today, and then the first part of next class is going to be a worksheet kind of working over problems from here. Okay, all right, you guys are with me. I just want to end today with getting into things called curl and divergence. Now be careful. I want to make sure. I just heard somebody say something interesting. There are no infinite sums here. There's no series, right? There's no sums or something. Is that what you're worried about?
Yeah.
We're not root testing things. Okay. You with me? I'm not shitting on that either, because personally I love that shit, but I know students normally hate that stuff, but it's awesome stuff. But we're not doing that. Don't worry. Here, divergence is going to mean, so if I think I was talking about this before, if I had a fountain spitting water out and it was just flowing away from it, that would be an origin point for water. So the divergence at that point would be positive because it's flowing away from that point. If it was a drain, it'd be negative. It'd be flowing into that point. So it'd be no conversion. No. It would just have what kind of divergence? It would have negative divergence, right? So it's not a originator. It's a receptacle, right? All right, maybe. So that's all that word is for. It has nothing to do with this stupid movie. It's nothing to do with ratio test, root test, any of that stuff, right? Nothing. Well, not much. So at the heart of this, on one level of this could just be seen as playing around with some stuff we've used before. So we've done this. Remind me what this meant. And what is the del operator by itself? Now let's say in 3D. So it'd be d by dx I hat plus and then I'm just applying it to some function. So then I operate on that function and it creates a vector. And of course we know what we call the gradient, and it points in the direction so it's symbolic. So I think at that point I told you that this operator is its own thing in its own right. So we start to play with it. So what did we have before to check to see if something was conservative in 2D? I did dp dy. I had to check to see if it equaled dq dx, right? In 3D, cross terms, I got a couple more things to check. Now this is not why this exists. But this is a nice example of what this is. It's kind of a step up, a way to go from this check to 3D check. So if the curl of F, so this is what the curl is. The curl is del cross F. So if you want it, it depends on how much you actually devoted to coming up with your own way to do cross products, right? So whatever way you used before, you can use it again. If the way you used was throw something down and pray, if it worked a lot for you before, what the hell? Maybe, I don't know if you got much luck left over. Some of you guys hopefully wrote the matrix out, right? Or you just memorized the form it was in. So here the matrix would be, you would put that, and what's that? Yeah, it'd be d by dx. Do they have this example in here? Oh yeah. Forgetting something. IJK, of course. And then down here is going to be your PQR. So they do have this in the book. So that's fundamentally what we're doing. And then I showed you one example where you can repeat it, and then you can dial the diagonal. So I don't know if anybody actually does it that way, or you just remember how this thing is set up. But real quick, this comes out to be dr dy minus dq dz. By the way, one way to see that this makes sense, what part of the function, what part of f is related to I hat? Sure. But I mean, p, right? All right, so notice two things that don't show up in the x part of the cross product, because cross products are supposed to take you to the other side. So there's no x's in here and there's no p's up here. All right, so that could be a little thing that you use to help you memorize this if you wanted to just memorize the form. I don't know if you can tell I have not got this memorized. I just basically redo it every time I need it. And then this is going to be dp dz minus dr dx. So there's no y, there's no q. And then plus, where am I at? dq. Oh, they turned the r and the p around inside. Good catch. Right? So there should be a minus there for the determinant, but instead they brought it inside and turned this around for what it normally would have been. You guys see it? So if you guys got it? Cool. Plus, where to go? dp dy. Okay. Let's see if I remember. There was something we did back in the day, I can't remember. There was a little shortcut I had back when I first took this stuff, but I can't remember. It's too bad for me. It's the permutations, if I say that word. You guys, anybody know what permutations? P, Q, and R, there's a lot of ways to permute them. Oh, don't worry about it. So on one level is going to be very nuts and bolts. They're going to give you a function, and they're going to ask you to calculate the curl of it. So you just got to do this, right? Okay, so this should be pretty simple. If you remember how to just set this up, I give you a function, it's going to be simple to do, I would hope. Right? It's basic stuff. What's more interesting is, what else does this do? How does it interact with other things? Right? So for example, what would, if the curl of f is 0, what might that imply? That would mean that, for example, that would mean what's true about these two. They are equal. And what is dq dx equaling dp dy? Yeah. So that's the curl of f being 0 is the three-dimensional analog of this equaling this, because it also checks the cross derivatives, right? So in 2 dimensions, I just have to check that this is 0, that this equals this. But if the curl is 0, that's the check to see if Yes, that I'm working with a conservative vector field. I like it. I can't remember how long it takes for them to say that. Oh, there it is. Theorem 4. Now, let me tell you, let me put a big ass F here for a vector field. Is that cool? You guys can change that. Now, more generally, or I don't know, sideways from that, if it is conservative, what can I find for big ass F? Little f, that when I take the gradient of it, I get big ass F. So that means that this is always true. The curl of any gradient is 0. Do you guys see how that only makes sense? If I took a gradient of something, that means that little f exists, which means the answer is a conservative vector field. In fact, I think a while back we said that the gradient makes its own field, which is a conservative vector field. So of course this is true for anything. This is only true if that is a conservative vector field, if there is a little f that works. Okay, I like it. Blah, 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 blah. All right, cool. I was trying to find, there's a lot of decent videos that give, so one level this is very mathematical, obviously. It's always very mathematical somewhere. The other side of this is, what does this mean physically, right? So there's decent videos. I was trying to find, I couldn't really find a good one, but there's a pretty decent one. So you can imagine if I just set something floating down a river. Some of you guys might realize when I'm looking at water flow down a river, is it all the way across the river? Is the water going at the same velocity? In fact, you guys should know, like if water's flowing through a pipe, where's it going to be going the fastest if everything else is held constant? Down the center. What's going to happen at the ends, at the pipe walls, or in this case, at the banks of the river? The velocity is going to approach 0 towards the banks or the sides of the pipe. Are you guys semi with me? Which means the velocity vector flow basically looks like parabolic in a way. It's got a maximum in the middle and it goes to 0 at the end. So I like it. So if I put something in the water off to a side, it's just going to float straight down. No, it's going to actually have something in the velocity flow that's going to make it want to rotate around its own axis. So it's going to be moving in that direction, but it's also going to be rotating. Why? Because in this case, if I put it, here's the river. Here's the middle of the river. So if I put it here, velocity is faster here than it is here. So it's going to have this desire to do this. That is what curl measures. How much does the vector field, be it water velocity or whatever, how much does it make something want to rotate around its own axis? So the curl at a point describes what's happening at that point. We can say the curl of an entire vector field could be 0, could be constant, depending on what the vector field looks like. All right, I like it. So wherever the curl is highest, that's where it's going to want to rotate the fastest or the most around its own axis. So that's why very often it's called a vortice kind of function. You're looking to see where the vortices are, does that make sense? The eddies and all kind of stuff? No. Doesn't make any sense. So trust me, you got to go to YouTube or somewhere, YouTube, and just search for videos on curl. You get some nice animations. It's not time yet. I want to see One Punch Man explaining. Nothing like that. It's just explaining calculus. I want to create that. That'd be nice. So, just to complete this for today, this is the last thing we'll do. The divergence of F. This is what I was talking about being an origin point or like a receptacle point, right? Or things come into or go out of. Electric fields are like this, right? You have positive and negative charges. You have north and south poles of the magnet, stuff like that. So the divergence, that's what it sort of means physically, do things seem to be coming in or going out of this little area? Mathematically, it's of course like the last thing we can do. with it is going to be the dot product. Let me just keep this big F. So would it make any sense to say what's the curl of the divergence of F? Of course, because the divergence comes out to be a number at a certain point, right? And the curl requires it to be a vector. I like it. So that same old stuff is going to pop up. You got to look out for it. You got to remember dot products and cross products and their basic properties. It's going to come out in this homework. So what's this look like then? The del is, of course, all the partials. Yeah, so what's it going to look like? Partial of f with respect to x plus partial of f with respect to y plus. Yeah. So again, on one level, this could feel like somebody just saying, all right, well, what if you do a dot product between these things? Right? And on one level, it sort of was, probably at some point. But then you can start to say, what does this mean physically? Does this have some mathematical meaning? Can I use this somehow? But I think I've pushed it enough. If you look up Maxwell's equations, if you look up almost any equations of flow or something, you're going to see a lot of, you're going to see some divergence, you're going to see some curls in there. Trust me. So I can rewrite integral formats using divergence and curl in a more concise form. So that's one thing you can do with it. So that's plenty for today. I'll see you guys Wednesday.
Is going to be day of the final?
Day of the final. Yep. Oh, anybody not get their test back?
No.
Day of the next test, which is the final now. This is a good catch. Oh, there. I don't have a stapler today. I decided to leave it.
Can you post the homework?
Oh, I did.
You did?
Yeah,
You did?
this morning. Yeah. Just got to email me. Yeah.
I did 3 of them, so I did the 57, 58, and 60.1. I was like, no more, I'm not going to email them.
All right, that's a pretty good amount of work.
Okay. So
I got through 16. How far did I get up today?
So they're all
check.
there, right?
Not all, but I'll see how far I made it. I can't remember. 16.3, I think.
Yeah.
Yeah.
Okay.
Just email me. Yeah. Oh, we'll talk about it Wednesday, but I'm thinking it's going to be, yeah. I think it's going to be up through 16.3. This guy is not going to be intense. Probably be like 5 from each section. 1 from each section, yeah.
Just curious, I think you picked the last
You turned it in on the day of the test or the day of the review? Yeah. You turned it in